Another method of traversing a graph is to use the breadth-first search. BFS is based on the idea of traversing a level at a time. To make this a little easier to see, I've positioned the graph slightly different so that it has separate levels. These are still both the same graphs, as all the vertices are still connected to the vertices they were previously, and there are no new edges. The terminology is pretty much the same as with depth-first search. We still have unexplored and visited vertices, as well as unexplored and discovered edges. However, now we have cross edges instead of back edges. I'll explain the difference in a moment. First, let me show you how BFS works. Rather than using a stack to keep track of our current vertex, we will use a first in, first out queue. Again, it doesn't matter which vertex we start at, so I'll begin at E, marking it as visited and adding it to the queue. It also doesn't matter which unexplored edge we discover first. However, what does matter is that we visit all the vertices on one level before we move to the next level. Just for ease of demonstration, I'm going to move from left to right in each level. Similar to DFS, we mark the incident edge as discovered and mark the next vertex as visited, then added to the queue. Since we are using a queue, however, the first item doesn't change, so the vertex we are concerned with also doesn't change. Go back to vertex E and traverse a different unexplored edge. When E no longer has any incident edges that are unexplored, we remove it from the queue and have a new current vertex. When going from one visited vertex to another visited vertex, we mark the edge as a cross edge. We continue traversing through the graph, removing vertices from the queue when they no longer have incident edges that are unexplored. When the queue is empty, we have visited all vertices and edges in this connected component. It is possible, however, that there are still other vertices in this graph that are not connected that have not been traversed. Here, I repositioned the depth-first search graph to look the same as the one we just did. When arranged like this, we can see that the only way to go from a visited node to another visited node with DFS is to loop back around and move up to a vertex with edges that have not been explored yet. In other words, a back edge occurs when W is an ancestor of V in the tree of discovery edges. Cross edges, as seen in BFS, are edges between W and V where W is in the same or next level as V in the tree of discovery edges. Our graph didn't have any on the same level, so I added one here for demonstration. If we go back to the maze idea and arrange the vertices and levels, then traverse it using BFS, we can again find a path to solve it. One neat thing about BFS, however, is that the path we find will be the shortest path. We can see the previous path we found is right here. However, due to this cross edge, the traversal for the path stops because it knows that there was a method of reaching that point in fewer steps. So while both traversals can check for cycles, paths, spanning trees, and connectivity, only BFS will give a shortest path every time. DFS may, but it isn't guaranteed.